So if I told you to go look out your window tonight, just, look up at the stars, you'd probably feel incredibly small.
Yeah, that's the standard human experience, right?
Exactly. You look up at the unimaginable vastness, just this dark, empty theater of the cosmos, and you feel like a speck of dust in a giant room.
Right. A tiny, insignificant actor placed onto a stage that was built billions of years before you even got here.
Yeah, billions of years. But what if the bleeding edge of theoretical physics just proved that the actual room, doesn't actually exist?
It's a wild thought.
It is. What if outer space, that endless dark void you're looking at, is actually, well, what if it's inside you?
I know it sounds like science fiction.
Oh.
Maybe like deep mysticism. But what we're dealing with today is hard mathematical topology.
And quantum mechanics.
Exactly, quantum mechanics. When you actually trace the structural math of how a physical boundary is formed, the whole concept of the universe as an external container just completely falls apart.
I have to admit, when I first started reading through the stack of sources we have for this deep dive, my brain basically flatlined for the first hour.
Oh yeah, it's dense material.
It really is. But once it clicks, it is the absolute definition of a paradigm-destroying shift.
For sure.
We've got theoretical papers today combining cybernetics, holographic quantum gravity, and a 1969 masterwork by mathematician George Spencer Brown called Laws of Form.
A classic.
Plus this incredibly radical concept called the inverted observer locus model. Our goal is to take all this dense math and map the absolute basic logic of drawing a boundary onto the deep physical architecture of quantum tensor networks.
Right, literally just the cognitive act of separating one thing from another.
Right.
Which is an ambitious mission because we are essentially trying to reverse engineer reality here.
We are.
But the beauty of these sources is that they're all pointing toward the exact same thing, finding the most elegant, simple rules that govern everything from human perception to the fabric of space-time itself.
And as a massive payoff for sticking with us through the physics, we're going to use this model to completely, and I mean cleanly, solve the paradoxes of the infamous quantum double-slit experiment.
The holy grail of quantum mysteries.
Truly. We're going to break down why quantum wave collapse isn't some mysterious, ghostly physical event happening in a giant background room.
Right.
It's a primary cognitive act. But to get there, to understand how you are projecting the universe, we have to start at the very bedrock of logic.
We do?
Because if you want to build a universe from scratch, what is the absolute first step? Because according to our sources, it isn't a big bang of exploding matter.
No, not at all. The starting point of everything is a logical operation.
Okay.
And to understand that, we really have to talk about George Spencer Brown.
Right, from 1969.
Yeah. He was an English mathematician, an engineer, a polymath who worked alongside people like Bertrand Russell.
Heavy hitters.
Exactly. So in 1969, he published a book called Laws of Form. Now, Laws of Form is one of those texts that seems deceptively, almost comically simple at first glance.
But it isn't.
No, it shook the foundations of mathematics, logic, and cognitive science.
So what was the specific problem he was trying to solve back then? Like, why write this book in the first place?
Well, Spencer Brown was looking for the absolute bedrock of mathematics.
Okay.
Before you can have numbers, before geometry, before you can even have true or false, what do you need?
I mean, I'd assume you need things to count.
Right. But he realized that you can't start with things. You have to start with the action that creates a thing.
Oh, I see.
He proved mathematically that before you can have any system of logic or any physical observation, you have to begin with one single imperative instruction.
And what's the instruction?
Draw a distinction.
Draw a distinction. So literally just separating something from everything else.
Precisely. Let's ground this in something you do 1,000,000 times a day without even thinking about it.
Sure.
When you walk into a room and you see a coffee cup on a table, your visual cortex and your cognitive network are actively doing something.
They're drawing a boundary.
Yes. They're drawing a boundary. They're separating a specific cluster of visual data and calling it cup, while simultaneously pushing everything else into the background as not cup.
That makes sense.
If you can't draw a distinction, you cannot perceive a cup. You can't perceive anything.
Reality would just be this undivided, unconditioned soup.
Exactly, just a soup.
Okay, so observation isn't passive. I'm not just sitting here letting reality wash over me. I am actively slicing it up.
You're carving it out.
And in his math, Spencer Brown symbolized this active slicing using a symbol he called the mark, right?
Yeah, the mark. He drew it as a sort of cross or right angle, like a bracket.
Like an L shape almost.
Yeah, exactly like an L shape. But The profound mathematical insight here is what happens the exact millisecond you draw that mark.
Okay.
The moment a distinction is drawn in an unconditioned blank field, you instantly and simultaneously create three distinct things out of absolutely nothing.
Wait, three things.
Three things.
Because if I take a pen and draw a circle on a blank piece of white paper, I feel like I've just created one thing, a circle.
Right, that's the illusion. You haven't just created a line.
I haven't.
No. You've instantaneously created the inside of the circle, the outside of the circle, and the boundary itself that separates them.
Oh, wow. Okay.
You cannot have an inside without an outside.
Right.
And you cannot have either without the boundary defining them. They are co-created at the exact same moment.
That actually makes perfect sense. The boundary is what gives the inside and outside their meaning. Without the ink line, it's just blank paper.
Exactly. And from this single primal act of drawing a boundary, Spencer Brown established two primitive arithmetic laws.
Just two.
Just two. These two laws dictate how distinctions interact with each other. They are the absolute foundation of logic.
And the sources we are looking at refer to these two laws as the cosmic keyboard, right?
Yes, the cosmic keyboard, the fundamental keystrokes that write the code of reality.
I love that phrase. Let's figure out how this keyboard works. The first key, the first law, is called the law of calling.
Or condensation, yeah.
Right, condensation. The math notation looks like that. Well, for the listener, if you have the mark of a state called A, and you put another mark of A right next to it, it just equals the mark of A.
Right. The law of calling dictates that repeating a distinction is identical to making it once.
So calling it twice doesn't change it?
Calling a boundary twice changes absolutely nothing about the boundary.
Let me try to wrap my head around this with an analogy. Is it like, if I paint a wall red and then I paint it red again, it's still just a red wall?
That's close, but painting involves adding physical layers of matter. A better way to think about it is pure information instruction.
Okay, what about word processing? Think about formatting text.
Oh, that's a good one.
It's like clicking the bold button on your computer. If I highlight a word and hit the bold command, the word gets bolded. But what happens if I accidentally hit the bold command a second time while it's still highlighted? The computer doesn't freak out.
No, it doesn't.
It doesn't make the text double bold and break the font. It just stays bold.
That is a brilliant analogy. The computer system recognizes that the second instruction is entirely redundant.
It already knows it's bold.
Exactly. So it condenses that redundancy. It doesn't stack the operations infinitely. It just says, okay, the state is bold. I already know this.
It compresses it.
The system compresses the redundant instruction to enforce structural efficiency. If you point at a tree and say tree, and then point at the exact same tree again and say tree, you haven't magically spawned a second tree into existence.
Right, I'm just looking at the same tree.
You've just reinforced the original boundary you drew around the first one.
Okay, so the law of calling is nature's ultimate data compression. It condenses redundant boundaries into one. What is the second key on the keyboard?
The second key is the law of crossing, also known as cancellation.
Cancellation.
Yeah. The law of crossing states that if you cross back over a boundary you just created, you cancel the distinction entirely.
So it vanishes.
You return the system to its original unconditioned state.
So if you draw a circle and then you draw another operation that essentially crosses the line of that circle, the whole thing vanishes.
Mathematically, yes. Think about physical movement.
Okay.
If you step from the outside of a room to the inside, you've crossed a boundary.
Right.
If you turn around and step from the inside back to the outside, you've crossed it again. You are now back exactly where you started.
Oh, I see. The two operations cancel each other out.
Exactly.
Like a double negative in language. If I say, it is not true that it is raining, I'm drawing a boundary not true around another boundary raining, and the result is just, it is raining.
Exactly. The boundaries annihilate each other. The system returns to a state of transparency.
Okay.
So you have condensation calling redundant things as one, and cancellation crossing a boundary to return to zero.
All right, I'm with you on the logic. It's elegant. It makes sense. But here is my massive sticking point with this entire deep dive.
Let's hear it.
Why does a 1969 math book about how to draw logical brackets have anything to do with modern theoretical physics?
It's a fair question.
Because right now, this sounds like philosophy. How does drawing a boundary completely invert how we view the physical cosmos?
Because of what we touched on at the very beginning, that feeling of looking up at the stars and feeling like you are inside a giant room.
Yeah, feeling tiny.
Classical Cartesian science, which is the Newtonian physics we all learned in high school, assumes a very specific sequence of reality.
Okay, what sequence?
It assumes that the outside exists first. It assumes that physical space is a massive, pre-existing, objective reality, a giant empty box.
Right, the universe is the box.
And then, according to this classical model, the inside, which is the observer you, biological life,
Yeah.
a planet is just passively placed into that box at some random point in time.
Like filling up an aquarium with water and then dropping a fish in. The aquarium was already there.
Exactly.
Yeah.
But Spencer-Brown's math proves that this assumption violates the fundamental laws of distinction.
How so?
The inside and the outside must be co-created at the exact moment an observer draws a distinction. The outside does not sit there in the dark waiting for you to arrive.
Hold on, are you literally saying that the physical distance between my house and the grocery store, or the distance between Earth and Mars, isn't just empty space that's sitting there right now?
Yes, that's exactly what I'm saying.
Wait, really?
The math suggests that space, as an external physical reality, is generated as the exterior reflection of the boundary you are currently drawing.
Mind-blowing.
You, as a cognitive system, are actively carving reality out of the void using the law of calling and the law of crossing. Every time you observe a form, every time you measure the distance, you are executing these logical operations.
If this is true, if reality is literally built by these logical operators, then we shouldn't just be talking about abstract math. We should be able to pop the hood of the universe, look at the actual circuitry of space-time and quantum mechanics, and find these exact two keys, calling and crossing, running the hardware.
And we can, which is exactly where theoretical physics is right now. We have found the physical architecture of Spencer-Brown's math.
Okay, let's go there. Let's look at the quantum circuit board. The sources heavily emphasize something called MERA networks.
Yes, MERA.
And before you define the acronym, because I know it's a mouthful, let's set the stage for why physicists even needed to invent this concept. What problem in physics led to MERA?
It fundamentally goes back to Einstein and the problem of quantum entanglement.
Spooky action at a distance.
Exactly. For decades, physicists have wrestled with spooky action at a distance. The fact that two quantum particles can be entangled in such a way that interacting with one instantly affects the other, even if they are light years apart.
Because if they are light years apart, how is the information traveling instantly? It breaks the speed of light.
Right. It suggested that space wasn't as solid or fundamental as we thought. So in modern theoretical physics, particularly in a field called holographic quantum gravity and the ADS-CFT correspondence, physicists had a radical breakthrough.
What was it?
They realized that physical space isn't an empty container that particles live inside. Space itself emerges from quantum entanglement.
Emerges from it.
Entanglement is the thread that weaves the fabric of distance.
Okay, so space isn't the canvas. Space is the painting.
Exactly. Beautifully put. And physicists needed a mathematical way to describe exactly how a flat, highly dense boundary of quantum entanglement unfolds into a massive 3D spatial geometry.
And that's Arrowway.
That's where MERA comes in. It stands for Multiscale Entanglement Renormalization Ansatz.
I knew it was going to be a terrifying string of words.
It's physics. They love their acronyms.
Let's unpack it for the listener. What is it visually? If I could see a MERA network, what does it look like?
Think of MERA as a discrete visual circuit diagram. It looks like a hierarchical tree, like a massive family tree of data.
Okay, a tree.
The bottom layer of the tree is the highly dense, messy quantum boundary. And as you move up the branches of the tree, it generates the physical space of the universe.
Moving up builds the space.
Yes. But the most incredible part is what this entire universe-generating tree is built out of.
Let me guess. Two things.
Exactly, two primitive tensor blocks.
Just like our two keys on the cosmic keyboard.
Exactly.
Okay, but I need you to explain what a tensor is in this context, because I hear that word thrown around in sci-fi movies constantly, but what actually is a tensor in a quantum network?
For our purposes, think of a tensor simply as a data processing node.
A node. Okay.
It's a mathematical object that takes in information, applies a specific transformation to it, and spits it out.
Like a little factory worker.
Right. In MERA, the network is built by stacking thousands and thousands of these two specific tensor nodes on top of each other.
What are the two nodes called?
The first one is called a disentangler. The math uses the letter U to represent it.
The letter U. Got it.
And the second one is called an isometry, represented by the letter W.
Okay, let's look at what these nodes actually do to the data. Let's start with the disentanglers, the U-tensors.
A disentangler, as the name suggests, removes local, short-range quantum entanglement between adjacent sites in a quantum lattice.
What does that mean in plain English?
Well, when you have two quantum data points sitting right next to each other, their boundaries get incredibly messy and entangled with each other. It's noisy.
So the U-tensor acts like a sweeper. It cleans up the noise.
It does.
But how does it do that mathematically without just deleting the universe?
Because it is a unitary tensor. Mathematically, this is written as U dagger times U equals the identity matrix.
Whoa. Okay, pause.
Too much math.
Yeah, you can't drop U dagger times U equals the identity matrix without translating it. What is an identity matrix and why does it matter here?
Fair enough. My bad. In linear algebra, an identity matrix is basically the mathematical equivalent of the number 1.
The number 1.
Right. If you multiply a number by 1, it stays the same. In quantum mechanics, if a process results in the identity matrix, it means the operation is perfectly reversible.
Oh, I see.
No information is destroyed or lost. It is perfectly preserved.
So when it sweeps, it isn't throwing anything in the trash.
Exactly. So when a disentangler cleans up the messy quantum noise, it isn't deleting the data. It is applying a phase rotation that perfectly untangles the correlations while preserving all the core information.
It just tidies up the local boundary before passing the data up the tree.
Spot on. It tidies up.
Got it. It smooths the rough edges of the quantum data without losing the plot. Now, what about the second node, the isometries, the dip tensors?
Isometries are isometric blocks, meaning W dagger times W also equals the identity matrix.
So again, perfectly reversible, no information loss.
Right, but their job is different. Their job is coarse graining.
Coarse graining, like sanding would.
Like shrinking data. They take multiple quantum lattice sites, let's say 2 or 3 distinct, clean data points that just came from the disentangler, and they merge them together into a single, effective macro site.
They compress the state space.
Yes, they combine the data points, they look at the redundant quantum states, and condense them into one higher-level variable.
Wow.
And here's the magic of MERA. By simply applying a repeating sequence of these two actions, disentanglers cleaning up the local noise, and isometries compressing the data together over and over, layer by layer, moving up the tree, the math automatically generates the hyperbolic geometry of physical space.
This is where my brain starts to hurt in the best way possible.
It's a lot to take in.
Because normally I think of space as the empty void between things, the distance between my hand and the microphone right now.
Right, the empty room.
But if I'm understanding you, the distance between my hand and the microphone is literally just the result of this tensor network compressing data.
That is exactly what holographic quantum gravity tells us.
That's insane.
Distance is not an empty vacuum. Moving farther away in physical space doesn't mean moving through a void. It means looking deeper into the tensor network, into higher layers of the tree where the quantum information has been more heavily coarse-grained and compressed.
So when I look at a mountain range that is 50 miles away, it looks smaller and less detailed to my eye, not because it's far away in a giant box, but because the visual data of that mountain has gone through billions of isometry tensors compressing the data.
Yes. What physicists call the renormalization group scale step, the process of mathematically zooming out and blurring the fine quantum details, literally translates into emergent spatial distance.
Distance is data compression.
Distance is data compression.
That is staggering. If distance is data compression and reality is a circuit board of these U and NV tensors, we have to map our logical keyboard directly onto this.
Let's do it.
Let's connect the 1969 math of Spencer Brown to the modern quantum MERA network.
It's a perfect, mathematically rigorous one-to-one mapping, an isomorphism.
Okay, let's look at the isometries first. The tensors in ERA that merge multiple data sites into one. What does that sound like from Spencer Brown?
Well, what do you think?
That is exactly the law of calling, condensation.
Precisely. Just like calling a distinction twice condenses into a single mark, the isometry tensor condenses redundant local quantum states into single higher-level macro variables.
Just calls them as one.
If the MERA network didn't have isometry tensors, the quantum information on the boundary would proliferate infinitely outward. It would be an unmanageable explosion of data.
Just infinite noise.
The isometry enforces structural efficiency by calling redundant states as one. The U-tensor is the law of calling in physical form.
Which means the disentanglers, the U-tensors that clean up the noisy boundaries, have to be the law of crossing, cancellation.
Exactly. A disentangler acts on the shared boundary distinction between two adjacent quantum sites. It applies that unitary inverse operation, that reversible math we talked about, which effectively crosses back over the mark to cancel out the short-range entanglement noise.
It uncrosses the messy boundary to return it to a clean state.
You've got it.
Okay, I want to try and build an analogy here collaboratively because I need to visualize this compression. Let's say I have a massive, incredibly high-resolution digital photograph,
Okay, I'm with you.
like a 10 GB raw image file. I can't email that. I have to compress it into a JPEG file.
Okay, a JPEG compression algorithm is a great real-world parallel. Let's walk through it. What happens when the algorithm looks at the raw pixels?
Well, in a raw image, every single pixel has its own unique boundary of data. If I take a picture of a blue sky, there might be millions of pixels, and no two are exactly the identical shade of blue.
Wait, it's noisy.
It's incredibly noisy data. So the JPEG algorithm first has to look at the boundaries between those pixels.
And that is your disentangler, the law of crossing.
Okay.
The algorithm looks at the jagged, messy, microscopic boundaries between those slightly different blue pixels, and it crosses them out. It applies an operation to cancel the noise and smooth the gradient.
Right. And once the noise is crossed out, the algorithm looks at a block of, say, 16 pixels that are all now virtually the same shade of blue.
Yeah.
It doesn't need to save the data for 16 individual pixels anymore. It merges them into one single blue macro block.
And there's your isometry,
Yeah.
the law of calling. It condenses the redundancy, says blue, 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 blue. Okay, I get it. The state is blue. I'm just going to call it once.
Wow.
Bam.
And if you apply that JPEG compression algorithm, disentangling the noise and calling the redundant colors as one over and over, layer by layer, you build the macroscopic image.
Exact.
It shrinks the file size down to 2 megabytes so you can actually perceive the whole image on your screen.
And in physics, when you apply the law of crossing the disentangler, followed by the law of calling the isometry over and over in a quantum tensor network, you literally build the macroscopic geometry of reality.
That's beautiful.
The geometry of physical space is nothing more than the physical execution of Spencer Brown's logical laws running on a quantum substrate.
So, if space is just a compressed interface of internal logical operations, where are we?
What do you mean?
Because normally I think of myself as being inside space, but if space is just the projected rendering of this compression, this completely destroys the idea that we live inside a giant, infinite physical box.
It forces us to invert our entire model of the cosmos, which brings us to the inverted observer locus model.
Let's get into it.
This is where we have to fundamentally rewire how your brain pictures infinity.
Let's do the rewiring. Contrast this with how we normally think.
We normally operate under the classical axiom of realism.
Right.
Classical realism is that persistent, deeply ingrained belief we open the show with. It's the belief that space is a massive external container stretching out into physical infinity in all directions.
Yeah.
And biological life, you, the observer, is just a small, finite, temporary accident that spawned inside of it.
The ultimate external view. We are just finite specks of dust in an infinite void.
But the inverted observer locus model flips this topology completely inside out.
Inside out, how?
In this model, the finite observer, the biological and cognitive system that is drawing the boundaries, is the primary container.
Wait. If I am the container, if my biological cognitive system is the boundary, where does the rest of the infinite universe go?
It goes inward.
Inward.
Infinity doesn't exist as an outward physical distance stretching endlessly away from you.
Yeah.
Infinity exists as continuous internal mathematical division.
Okay, you're going to have to explain internal mathematical division because my brain is still stuck in the giant box. How can infinity be internal?
Think about it through set theory and pure mathematics.
Okay.
If you take a closed, finite Fagel interval, let's say a piece of string that is exactly 1 inch long, or mathematically, the space between the number 0 and the number 1.
Right.
How many decimal numbers exist in that 1 inch space?
Well, there's 0.1, 0.01, 0.01, 0.001. I mean, I could keep adding zeros forever. So there's an infinite amount of numbers between 0 and 1.
Exactly. It is an uncountable infinity. Mathematicians call this the cardinality of the continuum.
Cardinality of the continuum.
All right. It's written as 2 to the power of a left null. What this proves mathematically is that you can have an infinite amount of structural complexity and information depth existing entirely contained within a bounded finite space.
Because the boundaries are 0 and 1.
Exactly. They are finite. You could hold the 1 inch string in your hand. But the internal depth of that string is infinite.
So applied to us, the finite biological boundary of the observer, like my brain, my visual field, holds an infinite internal data depth.
Yes. And under this inverted model, what you perceive as outer space is not a pre-existing physical room.
It's not the box.
It is the external holographic boundary projection of your own internal infinite subdivision. You are projecting the depths outward.
Okay, the sources mention a geometric proof for this that I really want to explore. They use something called stereographic projection and the Poincare disk model.
Ah,
Can you
yes.
walk me through a thought experiment of how this works? How does geometry prove that a finite boundary can actually feel like an infinite outer space to the person inside it?
The Poincare disk model is one of the most beautiful mathematical proofs of this concept. I want you to imagine a perfectly flat disk, like a circle drawn on a piece of paper.
Got it.
To an external viewer looking down at the piece of paper, the disk is obviously finite. It has a strict boundary, a set radius.
Right, I can see the edge of the circle.
But now imagine you are a tiny 2D creature living inside that circle.
Okay, I'm in the circle.
The metric inside the disk, the mathematical rules for how distance is actually measured by someone navigating it, is non-Euclidean.
What does that mean for me, the tiny creature?
It means the metric changes as you move outward from the center toward the edge.
How does it change?
The metric scaling factor shrinks your measuring stick, and it shrinks you the closer you get to the edge.
Shrinks me.
Yes. So let's say you start walking from the center to the boundary. At first, you cover ground normally. But as you get closer to the edge, your size shrinks by half, and your stride shrinks by half.
Wow.
You take another step, and you shrink by half again.
So from my perspective, inside the circle, my steps feel the same. But to the outside observer looking down at the paper, I'm taking infinitesimally smaller and smaller steps.
Precisely. Because your internal measuring stick is shrinking relative to the global boundary, the distance in front of you stretches exponentially.
That's crazy.
As you approach the physical edge of the disk, the mathematical distance you have to travel approaches infinity. It would take you infinite energy and infinite time to ever reach the physical edge of that circle.
That is mind-bending. So to me, the person living inside the universe feels completely unbounded, infinite, and endlessly vast. I would look out and see an endless void.
Exactly.
But from a purely topological, global standpoint, I am completely bounded within a finite radius.
The boundary is finite, but the internal experience of navigating to that boundary is infinite. Our sources use a great physical analogy for this regarding scale. Think about standing on the surface of the sun.
Okay, assuming I have a very, very good spacesuit.
Right, highly theoretical. Globally, looking at it from orbit, the sun is a finite, bounded sphere. It's a ball.
Yes.
But to a tiny, localized human observer standing directly on its surface, the curvature of that sphere completely vanishes.
Because it's so big.
Because of the massive scale difference between the observer and the container, the local horizon flattens out entirely.
It would just look like an infinite, unbounded, flat plane of fire in every direction.
Right. It gives the absolute illusion of an endless external space. And that is what outer space is.
So outer space is an illusion of scale.
When you look through a telescope at a distant galaxy, you are not looking far away into a physical box. You are experiencing the vast data capacity of your own internal rendering engine.
Your own internal rendering engine. I love that.
The vast scale of space reflects the infinite mathematical divisibility of your internal state space, rather than an endless physical field.
I just want you, the listener, to pause for a second and look at the room around you. Really look at the depth of the room.
Yeah, take it in.
Under this inverted model, you aren't looking at an empty room that happens to contain you. You are looking at your own cognitive engine's boundary interface. You are projecting your own infinite internal state space outward, layer by layer, through those MERA tensor networks.
It is a profound epistemic phase shift.
Face.
The observer shifts their core identification from being a small, physical avatar wandering around inside a dead universe to realizing they are the active locus generating the spatial geometry itself.
It's beautiful, but what's genuinely fascinating here is that our sources claim this doesn't just change our philosophical perspective. This isn't just a fun way to think about the universe.
No, it has practical physics applications.
This exact topological inversion physically solves paradoxes. Specifically, it perfectly mathematically solves the most infamous, baffling mystery in the history of physics, the quantum double-slit experiment.
Which is the holy grail.
The absolute holy grail.
The double-slit experiment has given physicists headaches for 100 years because it breaks classical reality. But to appreciate the solution we are about to offer, we have to meticulously review the problem.
Let's do it.
We have to walk through why the standard double-slit experiment is such a paradox under the classical empty box view of the universe.
Let's set the stage. The history of this experiment goes all the way back to Thomas Young in 1801, but the modern quantum version is what we really care about today. Walk us through the physical setup in the lab.
The setup is deceptively simple. You have a particle gun, like a laser that can fire single photons or single electrons, one at a time.
Okay, a particle gun.
In front of the gun, you place a physical barrier, like a metal plate. And in this metal plate, you cut two tiny parallel slits, just two narrow doors.
Left door, right door.
Right. Finally, behind the metal plate, you place a detection screen, like a piece of photographic paper, that will record exactly where the photon hits.
So I fire a photon, it goes toward the plate with two slits, and it hits the screen in the back. If I am thinking classically, like a Newtonian physicist, I'm firing a tiny, solid bullet. So what should happen?
Classically, if you fire thousands of these tiny bullets at the plate, most of them will bounce off the metal. But some will happen to go through the left slit, and some will go through the right slit.
Yeah, true.
So on the detection screen at the back, you should just see two solid bands of impacts directly behind the two slits. Just two stripes.
But that is not what happens.
No, not at all. When you fire quantum particles, even one by one, so they can't possibly bounce off each other, they don't form two stripes.
What do they form?
Over time, they build up an interference pattern on the screen. A pattern of many alternating dark and light bands spread out across the entire screen.
And an interference pattern is the classic signature of a wave. Like dropping two pebbles into a pond and watching the ripples crash into each other.
Exactly.
Where the crests meet, the wave amplifies into a bright band. Where a crest meets a trough, they cancel each other out into a dark band.
Which implies something entirely impossible for a solid bullet.
Right.
It implies that the single indivisible photon somehow traveled through both physical slits at the exact same time, acted like a wave rippling through a background space, interfered with itself, and then magically crystallized back into a single dot when it hit the screen.
It's baffling. How can a single particle split in half, go through two doors at once, and then reunite? Standard physics just shrugs its shoulders and says, well, it's a wave of probability moving through space. They call it the wave function.
Written as psi of x.
Psi of x.
But that explanation assumes the wave is moving through the external, empty box of space. Let's reframe this entirely using the inverted observer locus model. How does the wave function change if space isn't a box?
This is the crucial flip. In the inverted model, the photon is not a physical object moving through an external physical room. That is the fundamental error classical physics makes.
Precisely. If the universe is generated from the inside out, then before a final observation is made, the particle resides entirely within the observer's unconditioned internal state space.
So it's existing in that infinite, uncountable continuum we talked about earlier, the space between 0 and 1?
Yes. It is pure, uncollapsed probability density inside the cognitive locus.
Inside.
It has no physical spatial coordinates yet, because no distinction has been fully drawn to project it into outer space.
Okay, but if the wave isn't physically traveling through space, what on earth are the slits? Because in the lab, they look like very real physical holes in a metal plate. I can touch them.
They appear physical to the macroscopic observer, sure, but in the mathematical rendering of the event, the slits are not physical holes in an external void.
Because outer space is just the projected interface.
Exactly. In the underlying logic, the slits represent a dual-path distinction operator applied to the internal state space.
A dual-path distinction operator, let's translate that.
Mathematically, it's an operator applying distinction path, 1 union distinction path 2. Think back to Spencer Brown. You are applying a logical choice to the internal data. You are offering the data two possible boundary states.
But I'm not forcing it to choose one yet.
Exactly. Because no final measurement, no actual distinction occurs at the slits themselves. The photon passes the operator without a choice being made. So the operator yields an oscillating superposition. The internal states continuously interfere with one another entirely within the internal logical continuum.
Because no boundary has been drawn to separate them.
Yes. They are undistinguished. Because the law of crossing hasn't finalized a state, they remain a fluid continuum of probability.
They overlap.
They overlap and interfere because there is literally no logical boundary preventing them from doing so.
But I have to ask the obvious physical question. If the wave isn't physically traveling through space and the internal logic states are just interfering with each other in my brain's math, what is actually hitting the screen at the back of the experiment to make the pattern?
That brings us to the actual mechanism of wave function collapse. Let's define what collapse actually is under this new model, because it completely solves the crunch.
Right, the crunch. In standard physics, collapse is this almost magical, violent event. You have this giant spreading wave of probability moving through space, and the millisecond it touches the screen, The entire wave instantly crunches down into a single, tiny, localized particle.
And classical physics has never been able to explain a physical mechanism for that crunch.
Because it's impossible.
Right. Because if it's a physical wave spread across space, how does the left side of the wave know the right side hit the screen instantly faster than light so it can all collapse together? It violates relativity.
It's Einstein's spooky action again.
Right. Under the inverted locus model, there is no crunch.
None.
Because there was no physical wave in space to begin with, wave function collapse is not a physical wave crunching down in a room.
So what is it?
It is simply the primary cognitive and observational act of drawing the mark.
Drawing the Spencer-Brown distinction mark?
Yes. The detection screen at the back of the experiment acts as the final boundary interface. It forces the system to finally map the continuous, undistinguished internal depth to a concrete, discrete coordinate on the external projection.
So the interference pattern we see on the screen
Is simply the spatial rendering of undistinguished internal state interference projected onto the external 2D interface.
Wow.
The cognitive locus hasn't drawn a boundary to distinguish path A from path B at the slits, so it simply projects the ambiguous interfering data directly onto the boundary screen. The pattern is just what ambiguity looks like when it's forced to render spatially.
Okay, this sets up the absolute knockout punch for the most baffling part of the experiment, the which-way paradox. The which-way paradox is what keeps physicists up at night pulling their hair out.
Let's walk the listener through it. What happens when physicists decide to get clever?
Right. Physicists look at the interference pattern and say, okay, this photon is somehow going through both slits. Let's spy on it. So they place a microscopic detector right at the slits to watch the photon and definitively measure which way it actually goes. They want to catch it in the act.
And what happens in the lab? Physically, the moment you turn that detector on?
The interference pattern on the back screen instantly disappears completely. It vanishes. And suddenly you just get two solid bands of particle impacts, exactly like the classical bullets. Just by looking at it, just by measuring which slit it goes through, the system completely stops acting like a wave and acts like a classical particle. It's as if the particle knew you were watching and changed its behavior.
Which has led to decades of endless mystical speculation. You get pop science articles claiming that human consciousness actively alters physical matter across the room, or that particles can travel backward in time to change their path.
Yeah, lots of wild theories.
But we don't need mysticism. We don't need retrocausality. We just need Spencer-Brown's law of calling.
Condensation.
Yes. Let's track a single photon in the lab under our new model. What does placing a detector at the slit actually do in terms of the logical topology?
If the slits are a logical operator, placing a detector at the slit forces the cognitive locus to register a distinction early. You are demanding a measurement. You are drawing a boundary before the system reaches the final projection screen.
Exactly. By placing the detector and turning it on, you draw the mark at the slit. Now, what is the mathematical rule for the law of calling?
The law of calling says that applying the mark operator to a state that is already being marked condenses it. Mathematically, the mark of x equals the mark of x.
Yes. Drawing an explicit distinction at the slit resolves the internal duality early. You force the system to call the state.
It calls the state. The interference pattern on the back screen vanishes because the internal ambiguity was eliminated at the first distinction mark.
Exactly.
The internal states stop interfering with each other because you drew a hard logical boundary between them before they could reach the final projection screen.
It is so incredibly clean. It is mathematically perfect. We no longer have to invent mysterious physical forces collapsing waves. We don't have to break the speed of light with a collapsing physical wave. We just apply the fundamental logic of distinction.
Amazing.
If you draw the mark early at the slits, you condense the state early, and you get two solid stripes of particles.
And if you don't draw the mark at the slits, the undistinguished state space retains its internal ambiguity and projects that interference directly onto the boundary screen. There is no paradox.
No paradox at all.
The paradox of quantum mechanics only exists because we stubbornly insist on putting the observer inside the box instead of realizing the observer is the box.
The math of Spencer-Brown and via tensor networks shows us that the universe is actively built by observation. The physical universe is the external signature of your own cognitive architecture processing internal probabilities.
It's profound. So as we wrap up this deep dive, let's summarize the massive paradigm shift we've just walked through. We started with a universe that was a dead, empty container, and we have completely dismantled it.
We have. By looking at quantum tensor networks, specifically how MERA uses disentanglers to clear noise and isometries to compress data, we map that physical geometry directly to the foundational logic of boundaries developed in 1969.
Right.
Space isn't a vacuum. It's a structural network.
A network built by the observer, condensing and crossing out information. And wave function collapse isn't a physical crunch in a room. It's simply the act of drawing a boundary in your own infinite internal state space.
But there's one final piece of Spencer Brown's math that we haven't touched on, and I think it perfectly frames the implications of everything we've discussed today.
The sources mention a final concept called re-entry. What is it?
We talked about the law of calling and the law of crossing. But Spencer Brown realized that in complex systems, a distinction can be placed inside its own space.
Inside itself.
Mathematically, it's written as a function feeding into itself. F equals the mark of F over the boundary. It is a system observing its own boundary.
According to the cybernetic models in our stack, when a system does this, when a distinction re-enters its own space, it creates a logical paradox that can't be resolved statically. It causes the boundary to infinitely oscillate. It fluctuates constantly between state and non-state.
And in Spencer Brown's calculus, that infinite oscillation produces the mathematical experience of time and dynamic motion. Time is the oscillation of a boundary observing itself.
So if that's true, then perhaps the apparent expansion of the universe, the movement of galaxies, the relentless flow of time itself is nothing more than you, the localized cognitive observer, continuously re-entering your own distinction.
Right.
You are not moving through a static universe. The universe is the physical signature of your mind moving through itself.
It's a breathtaking realization. You are the engine of the cosmos.
It really is. Thank you for joining us on this deep dive. The next time you walk outside and look up at the night sky, or even just look across the room, try not to see it as a vast, empty void that you happen to be sitting inside. Remember the math. Remember the compression. See the space around you for what it truly is, the active, unfolding frontier of your own perception.